Hello and welcome again to another lesson on vectors, the fourth one in fact, of this series. So today we're going to take forward what we know already about vectors and apply it to some geometric problems which we can solve using nothing more, weirdly, than abstract vectors to solve real problems, including, for example, where the diagonals of a parallelogram cross over, where they intersect. So we're going to see that later today. First of all, there are some warm-up questions for you to have a go at, as always. Here they are. So if you could attempt these four, and then only check your answers afterwards when you've had your best attempt and effort on your own. So pause the video, try these on some paper, and check back here when you're ready to see how you've done. Okay, if you've done that, let's have a look at question 1 together. So question 1, we're given that A is 3i minus j, and B is minus 5i minus 2j. We have to find the exact value of the magnitude of A minus B. So for part A, what we need to do first of all is to work out what A minus B actually is. You can do this in I and j form or in column vector form. It really doesn't matter, whatever your preference is really. So I'll do it in both ways so you can see. My preference happens to be column vectors. So A as a column vector is 3i minus 1j. And we're going to subtract from that B, which is minus 5i minus 2j. So, as a new column vector, we get 3 minus minus 5, which gives us 8, because minus minus 5 is plus 5. And on the bottom, for j, minus 1 minus minus 2 means minus 1 plus 2, which is 1. So, if you wanted to do this as a I and j form vector, I'll show you how this works now. So what we would have done, first of all, is wrote A in I and j form. So that's 3i minus j. We minus from that B, which is minus 5i minus 2j. So exactly the same arithmetic procedure, just written in a different way. So now, 3i minus minus 5i, collecting the I components, gives us 8i. And minus j minus minus 2j is minus j plus 2j, which gives us plus 1j. So the coefficients of 8 and 1 are still the same as they are here. So there's no real difference. The only difference is just how it's represented. Now what we must remember is how to work out the magnitude of a vector. So we worked out the new vector, which is A minus B. We have this. To work out the magnitude of the vector, we square the I component and add to that the square of the j component and then square root that whole thing. So it's going to be the square root of 8 squared plus 1 squared. And so on your calculator or otherwise, you should find that this is the square root of 65. Now for part B, I've got this arrow in the way slightly, so I'll just move this arrow down so you can see it. There we go. We need to find the unit vector in the direction of A minus B. So again, trying to remember from last lesson, to find a unit vector in the direction of a known vector, we just simply divide by the magnitude of the known vector. And so a unit vector in the direction of A minus B is going to be A minus B divided by the magnitude of A minus B. And so A minus B, the magnitude of that was root 65, and so we're going to divide through by root 65. So we can say it's 1 over root 65 of the vector A minus B, which is 8i plus j. And that's how you'd write it in I-j form. So that's all we need to do for question 1. Question 2, we've got 3 points given relative to a coordinate grid. We have 1, 1, 3, 3, and 5, 1. And we're told that these are vertices, they're corners, of a square. find the fourth vertex, or in plain English, find the fourth corner. So what I would suggest we might want to do for this is to just sketch out a coordinate grid to begin with. So here's one I had from earlier. So what we can do here is just sketch on the points roughly as accurate as we can be. So 1, 1 is going to be 1 along, 1 up, let's say about there. 3, 3 is going to be 3 along, 3 up, let's say about here. And the last one given is 5 along and 1 up, which, I don't know, might be somewhere like this. So now if we just take the time to actually have a look at what we've got, we can sort of make an intelligent guess as to where the other point must go. So these are the 3 corners of what we're told is a square. So I don't know about you, but I would argue that it's relatively obvious to consider that the other point must be like this somewhere. Somewhere down here. Okay, so let's label in the points just so we're not guessing and we're sure what we're doing. That's 1, 1. Here we had 5, 1. This one up here was 3, 3. So let's just think about the diagonals of this square. So if I just sort of sketch on from this corner to the opposite corner, that's got a length of going from 1 to 5. That should say 5, 1. It's a bit hidden, this one, so there we go. So from 1, 1 to 5, 1, that's a length of 4 across. Okay, so this is a length of 4 going along. And because it's a square, the length from the other opposite 2 corners should be 4 as well. And so if we just add this in the same way, we should see that the distance from this corner to this one below must be 4 also. So from this corner to that one was 4 along. From this one to the one below, that'll be 4 directly down. And so 3, 3, 4 below this will be at the point 3 minus 1. Using the fact that the diagonal distance from one corner to the opposite corner is the same for each pair of opposite corners. So from 1, 1 to 5, 1, that was a distance of 4. Using symmetry as well, the other corner which wasn't given to us will be halfway between 1 and 5. Will be directly below this point, and 4 below this one will be 3 minus 1. Part 3. Prove that 1 over cos theta minus cos theta is the identity of sine theta tan theta. So to prove identities, what we need to do is just start with one side and prove that it's identical to the other. And so we're going to start with the left-hand side. I'm just going to call this LHS, which stands for left-hand side. Oops, computer's going slightly slow so far, but we won't use that as an excuse. So this left-hand side, we have 1 over cos theta minus cos theta. So what I'm going to do here is I'm going to rewrite this as a fraction with a common denominator of cos theta. So this will be left just as 1 over cos theta. This bit won't change at all because it already has the correct common denominator of cos theta. However, what I need to do with the minus cos theta is to multiply it by itself to give cos squared theta and divide it by itself. So essentially multiply by cos theta over cos theta. Now what this will do is this will have the impact of making me able to write the numerator all over a common denominator of cos theta. So the numerator will become 1 minus cos squared theta, and then we'll have over cos theta at the bottom. However, what we need to do now is remind ourselves of an important trig identity from before. And so, if we recall that sine squared plus cos squared equals 1, this can be rearranged. So the identity, the main one, is sine squared plus cos squared equals 1. Therefore, if we just subtract sine squared from both sides, if we subtract cos squared from both sides, we see that sine squared theta will be the same as 1 minus cos squared theta. And so we can replace the 1 minus cos squared theta with sine squared theta. Now, this can be rewritten as well, which we'll do at the next step actually. So I'll leave it as sine squared theta for now, over cos theta. Now if I just rewrite sine theta squared as sine theta sine theta, and divide it by cos theta. What I'm going to do now though, I'm just going to divide the cos theta over here, then multiply by sine theta after. And again, we need to remember another trig identity. This one is another big one which you need to know off by heart, and that is that tan theta is sine over cos. And so this helps us to replace the sine over cos with tan, because tan is sine over cos. So then finally, sine over cos is tan. We have that times sine theta. So we have sine theta multiplied by tan theta, which is the same as the right-hand side, which is what we wanted to prove it was. And so that does it for us. So now we can have a look at the final warm-up question, question 4. Question 4, we're talking about the binomial expansion. We've got the coefficient of x cubed in the expansion of 2x plus a to the power 5 is 720. So find the possible values of a. So if we recall the binomial expansion, how we do it, okay, it's a power 5. So what we do is, because the power's 5, we put 5, choose 0. Now I'll do the terms up to the terms in x cubed, not skip ahead straight away, just so you can see the general pattern. So 5, choose 0. Then we have 2x. First of all, it's 2x to the power 5. Okay, so it's 2x to the power 5. A to the power 0. The power of the second thing in the brackets will always be the same as this number at the bottom of the n choose r. I'll come to this in a moment. Moving on, 5, 0 becomes 5, 1. And each time we move along each term, the power of the first thing, which in this case is 2x, drops by 1. So rather than 5, the power now becomes 4. And the power of the second thing, the a, goes up 1. So 0 plus 1 is 1. And continue the same way. So the next one, the power of 2x will drop to a 3, and the power of a will raise by 1 yet again to a 2. And we carry on more than this until we get to a to the power 5. But the only thing we're told here, the only thing that matters really, is about the coefficient of x cubed. So the coefficient of x cubed will be from this term here. So the coefficient of x cubed we're told is 720. And according to this, we can work out the coefficient of x cubed by using our calculator. So what we do is we do 5c2. The way we do this, if you remember, is we type the first number, so 5, and to get c, we do shift, then the division button, then 2. and that'll give us whatever. So we can press it now if you want, equals 10. Then we need to multiply this by 2 cubed, which gives us 80, and then we multiply that by x cubed and a squared, which of course we don't know what those are. But the 5 cubed 2 is 10, and the 2 cubed is 80, so that's enough. So in this x cubed term, we see here that we get 10 times 8, which is 80, a squared, x cubed. And so the coefficient of x cubed here, the stuff in front of the x cubed, is 80 a squared. So therefore, this coefficient, which is 80a squared, must equal 720. And that's our way into solving it. So therefore, 80a squared equals 720. Divide through by 80. We see that a squared must therefore equal 9. Square root both sides. We see that a must be either 3 or a maybe minus 3. So those are the two possible solutions, which concludes our warm-up. So now let's have a look at the main body of this session. Position vectors. Position vectors are vectors giving the position of a point relative to a fixed origin. This origin is almost always the origin you're already familiar with, the origin on a coordinate grid, which is 0, 0. So here's a representation of a position vector. So the position vector of point A, we'd call that the vector OA, where O is the origin. We put a line under it, which just denotes that it's position vector as we move from O to A. In numerical form, it would tell us how far along and how far up we'd have to go to move from the point of reference, the origin, to the endpoint A. So if OA is AI plus BJ, in other words, A units to the right and B units up, then the position vector of A is just AB as a column vector, which isn't too surprising. You should know by now in column vector form, for example, translating shapes or graphs by a column vector. The top number tells us how far we move to the right of the positive x direction, which is the same as the direction of the unit vector I, and the bottom number b tells us how many units we move in the positive y direction, which is the same direction as the unit vector j. Here's another diagram, which I'm just going to quickly explain. So we have here in red A, B. So from A to B, it's minus OA plus OB, where OA and OB are the position vectors of A and B, respectively. So I'm going to explain in a bit more depth why AB is minus OA plus OB. And in terms of solving geometric problems, it's like using a road map. So for example, you start at A, you want to go to B. So it might be you're at a place beginning with A. So I don't know, maybe geography is rubbish, isn't it? Maybe Arbourthorne, and you want to go to B, which is Bradford. There's no direct route from A to B. All you know is these two routes in black. So to go from A to B, all you can do is pick the routes you know. So before this was drawn on in red, we only had two vectors. So to go from A to B, what we could have done is we could have gone from A back to O, done a detour. So we could go from A to O, and then when we're at O, we could get the road map out again and think, oh, now there's a direct route from O to B. Like so. So the vectors are like roads. Okay, so that's from O to B. Now, if you're going from A to O, you're going in the same direction as from O to A, but the direct opposite way. You're not going from O to A, you're going from A to O. And so from A to O is the opposite. It's the negative version of the route as we'd move from O to A. Oops. Plus, of course, OB. So in a bit more depth, that's where this result comes from. Let's now apply this to a quick worked example using position vectors. So we've got points A and B on this diagram, which have coordinates 3, 4, and 11, 2. So find in terms of I and j, first of all, the position vector of A. So the position vector of A is simply, really simply as well, just going to be the numerical representation of this vector from O to A. So what is O to A in vector form? We need it in terms of I and j. So for O to A, how far along do we go? Well, because we've got the coordinates, we have to go 3 along, so it must be 3 in the I direction. And how far up do we go? We are going up. We're going 1, 2, 3, 4 up, which of course it tells us with this coordinate. So we're going 3i plus 4j. That's literally all there is to it. For part B, we want to work out the position vector of B. So for B, the position vector of B, that means from O to B. So starting at O, I'm going all the way along until we get to B here. So we give this in terms of OB, and it's just as easy as the position vector of A. So from O to B is 11 along, because the coordinates are 11, and we go 2 up from the origin, so plus 2j. Part C is where we use parts A and B, what we've done before. We need to work out the vector AB. So finally, we're working out this one, which is starting at A, how could we get to B? And it's one of these roadmaps sorts of questions. It's how do you go from A to B? We don't know a vector connecting A and B. We don't know a road. We don't know a vector, same thing. So what roads do we know which would allow us to move from A to B? Well, as you can see, these filled in vectors, these known roads, to go from A to B means we could start at A and go to 0. Then once we're at 0, we go from 0 to B. So if we're going from A to 0, that's the opposite way round. It's the minus version of going from O to A. Okay, so we know what O to A is. From O to A is this. So by thinking of AO in terms of OA, we can use this known result rather than having to do any more work. So we can use this to help us. Then of course plus OB, which we already worked out from before. And so once again, instead of using our brains too much and working out new things where we don't need to, we can just use this above. So what we have is minus OA. So AB is minus OA, which is going to be minus 3, 4. I'm substituting this in vector form for some reason. Never mind, I'll transfer it back. And plus OB, where OB is 11 to the right and 2 along. Minus 3 plus 11 is 8, and minus 4 plus 2 will give us minus 2. Of course, I made a bit of unnecessary work for myself. I need to change it back in terms of I and j form. So that's going to be 8i minus 2j. Now, it might be, and well done if you've spotted this, you might have spotted a much quicker way of doing it, and you might be thinking, why on earth has he just done it this really long way? You could have done this using the coordinate grid. From A to B, it's just this blue line. So how far along are we going? We're going 1, 2, 3, 4, 5, 6, 7, 8 along, and 2 down. So by inspection, you could have got 8i minus 2j. The reason I showed you this way is because in 99.9% of all cases, you need to know how to do this algebraically and abstractly. You can't always rely on a coordinate grid to help you out. For example, if these are really awkward numbers or huge numbers, you can't spend your time in an exam doing a massive coordinate grid and working out this way. So this way is good to visualize, but you need to move away from the specific, tangible way of doing it and take a step into abstraction and take this as a step towards doing it for any general case, for any vector, no matter how big or how small. So this is how you do it, and this is a method you need to be used to. This is just a way of representing what we're doing and proof that it works. Question 2 now. Another one on position vectors. We've got OA, which is 2i minus 5j, and AB, which is I plus 3j. We need to find, for part A, the position vector of B. So what I'm going to suggest we might want to do here is actually just sketch this out, because it does seem fairly hard to picture. I'm not talking even an accurate sketch, but just a rough idea of what's happening. So OA means we're going 2 along and 5 down. So it's quite steeply down here. So that's O. That's A. And then AB, starting at A and going to B, we're moving 1 along and going 3 up. So something like this perhaps. So the position vector of B, okay, that by the way is equal to OB. Okay, so what we want to find is OB. Which is this line here. So I'm hoping you can see now, for part A, to go from O to B, to go along to OB, using known vectors, we could detour from O to A first, and then from A to B second. If you notice, if the end letter, the end destination here, is the same as the beginning letter, the beginning destination here, then what we can essentially do is realize that the sum of these vectors, the combination, is just going from the first one to the last one. So if the end letter is the same as the beginning letter that we're adding on to, these two, in a very sort of loose way, cancel each other out. So we just go from O to B overall. So that's something to look out for in terms of realizing quick ways of doing it without having to draw diagrams. So OA, we've got OA here. OA is 2i minus 5j. And A to B, AB, is I plus 3j. So add the I components, so 2 plus 1 is 3, then minus 5 plus 3 is minus 2. So in IJ format, we have 3i minus 2j. For part B, we want the exact value of OB in simplified surd form. And so the magnitude of OB is simply going to be the square root of its I component, which is 3 squared, plus the square of its j component, sum the square of the I component with the j component and square it the whole thing. And so 3 squared plus minus 2 squared, 3 squared plus 4 becomes 9 plus 4, which is just simply 13, which won't simplify because there's no factor of 13 that's a square number greater than 1. And so the magnitude of OB is root 13. Question 3. We're now going to move on to solving geometric problems. So we have a diagram here. In the diagram, the points A and B have position vectors A and B respectively. The point P divides AB in the ratio 1, 2. Our task is to find the position vector of P. So for this one, we need to take the information we've been given here, that P divides AB in the ratio from 1 to 2. And so dividing AB into these different parts, that's one part. That's 2 parts. The whole thing was 3 parts in terms of ratios. 1 plus 2 parts is 3 parts. So from A to P is 1 part out of 3. From P to B is 2 parts out of 3. So this is 1/3 of the length from A to B. From P to B is 2/3 of the length from A to B. So what we're after here is a position vector of P. So in other words, we want to find OP. So let's think about this. We want to find a representation of this line here. So we could go whichever route we fancy. So we don't know any known vector along this route. So like the idea of roadworks, we need to use roads that are already given, that already exist, vectors we already know. So how can we get from O to P? Okay, well I'm going to show you actually 2 ways of doing this. Okay, one thing we could do is we could go from O to A. So from O to A is this vector here. And then when we've done that, we can go from A to P. So from A to P is this distance here. So now let's just think about what this is. So from O to A, by the way, we're going to give this answer in terms of vectors A and B. Okay, so OA is A. Now from A to P, that's just 1/3 of the vector as we go from A to B. Now this A to B isn't in the correct form, it needs to be in terms of vector A and vector B. So let's just think about what vector AB is. So how can we go from A to B? I'll put this in a bubble so you know it's just workings. From A to B, what we could do is we could go along from A to O. So we could go down here. When we get to O, we could go from O to B. And so from A to O, because that's the opposite direction from O to A, that's the same as minus OA, then plus OB. We can now give this in terms of the vectors A and B. So minus OA is minus A, and OB is just plus B. So we can sub in this to help us. So OA is A, we can leave this like this, plus 1/3 of the distance from A to B. So from A to B, like we worked out here, we said that's minus A plus B. So expand this out like we would do in terms of algebra. We get A plus 1/3 minus A. So 1/3 multiplied by minus A would actually be minus 1/3 A. Then plus 1/3 B. And so A minus 1/3 A would give us 2/3 A. Then plus 1/3 B. So that's the final answer. If you wanted to, by the way, this is completely optional. You could have factorised out the 1/3 and called it 2A plus B. So that, in my mind, is the easiest way of tackling this one. I will give you another way, in case you're interested. So you might be thinking, well, how did I know to go that way? The answer is I didn't. I just went some way I did know. How else could I have gone from O to P? So let's work out a different route and see if we got the same answer. So another option, so I'm going to call this method 2, because I'm not very inventive. I'll just call it method 2 because it's fairly obvious. Method 2, how else could we go from O to P? Well, from O to P, what we could have done instead, we could have gone from O to B. So we could have gone along here like so. And then when we got to B, we could have gone from B to P. So from O to B, as you can see, that's labelled by vector B. Now vector BP, BP is 2/3 of the distance from A to B. Okay, from B to P, or P to B, is 2/3 of the total distance from A to B. So it's 2/3 of AB in terms of distance. We've worked out AB, so let's stick with what we know if we can. However, from A to B is going from left to right. Because the direction we need from B to P is in the exact opposite direction, we're going along the route from B to A. So therefore we need to say it's minus this, because we're not going from A to B, we're headed in the direction from B towards A. So now OB is B, we can leave it like that. So we can say it's minus 2/3 of from A to B. Now AB is minus A plus B, which we worked out earlier. So A components first. So minus 2/3 multiplied by minus A gives us positive 2/3 A. Meanwhile B minus 2/3 of B leaves us with 1/3 of B. So as you can see, no matter which way we approach it, as long as we're careful with our expansion and simplifying, we will get the same results. I would say method 1 is easier. Method 2 just showed you, just so you know that it doesn't particularly matter which way you go, as long as you're careful of what you're doing and you pick your route sensibly. We're now going to have a look at solving some slightly harder geometric problems. So first of all, question 4. So we've got OABC is a parallelogram. So P is a point where the diagonals, which are given by these lines OB and AC, that's where they intersect. So the vectors A and C are equal to OA and OC, respectively. Prove that the diagonals bisect each other. Okay, so first things first, we just need to think about what we're doing here. So A and C are equal to OA and OC. So from O to A, let's just draw this on so we can make some sense of what we've got in front of us. So from O to A is that line here, and from O to C is going straight across like this. So I'm going to label this on. So that's the same as A, and that's C. Now we need to remember something basic and obvious about parallelograms, something you will have been told at GCSE. So what this is that the opposite sides of parallelograms are in the same direction and of equal size. So in other words, if this is A, we can say definitely that this is the same as A, and if this bottom one is C, then the top one will also be C. So in terms of proving that the diagonals bisect each other, what we need to do is think about two different routes from which we can start at O and get to P. So let's think about how we could do that. So one thing we could do to get from O to P, in fact I'll just divide the page so I've got enough space to work with without overlapping. So from O to P, we could go up to A, so we could go from O to A. And then we can go from A to P. Now, AP is somewhere along this line AC, but we don't know whereabouts it is. It could be halfway along, could be a third. We don't know. We can't go on the accuracy of this diagram. So we're going to say it's OA plus some multiple of AP. And so what I'm going to do here is I'm going to just call from A to P some multiple. I'm going to call it lambda. A lambda is some scalar, just some number of from A to C. So A to P is basically some fraction lambda of the distance as you go from A all the way to C. So it now begs a question of what AC is. So again, let's just put this in a little bubble somewhere. So from A to C, to go from A to C, we could go from A to O, and then from O to C. But from A to O is the opposite direction, the same distance but the exact opposite direction as we go from O to A. So this is minus OA plus OC, and so minus OA is minus A plus C, and so AC is minus A plus C. Okay, so now we've got this, we can replace AC with what it is in terms of A and C vectors. So OP equals OA plus some multiple of from A to C, some multiple of minus A plus C, because AC is minus A plus C. And I might as well replace OA as well. From O to A is A. So we've got A plus some multiple of minus A plus C, which I'm just going to call C minus A. Just put the positive thing first. So that's OP. Now let's think of another way we could have got to P. So let's think how else we could have gone from O to P using a different route, and as well as that, a different diagonal. So what we've been using here is AC. So we've already got it in terms of AC. Okay. So we've used AC. Let's now use something else. Then we can get, hopefully, something of a simultaneous equation, as it were. So we've used AC. Let's now try and incorporate the vector from O to B. Well, that's a bit too a thicker line. Purple's good, but we need a thinner purple, so this will do. So again, like I said, we don't know what multiple this lambda is. All we know is it's some multiple along AC. We're going to try and find out what it is, of course. We can also say that OP, it's along the length from O to B, so it's some fraction of the length from O to B. So it's OB multiplied by some fraction. Maybe it's like a third or 2/3 or a half. Let's call this fraction mu. Okay. Now, what we need to think about here is, how do we get from O to B? So again, let's think of it in this way. So from O to B, we could go along this one from O to C, and then when we get to C, we go from C to B. From O to C is C, labelled here, and from C to B is A. So that's what we can call OB. OB is C plus A. So in other words, OP is therefore some multiple, mu, looks like a weird M, it's called mu, it's a Greek symbol, some multiple of OB, some multiple of C plus A. So we've got two different ways of representing OP. Yep, so we've got this method for OP, which is this one here. We've got OP is also this. So what we're going to do now is we're going to equate these two bits. Okay? So we can now say that therefore A plus lambda lots of C minus A equals mu lots of C plus A. Now, as it stands, that doesn't really seem to help us, so what we can do, as outer algebra, we can expand it all out. So A, lambda times C is lambda C, lambda times minus A is minus lambda A, equals mu C plus mu A. So let's simplify this a bit more. Let's get the A terms so we can compare them, and then the B terms and we can compare those. So the C terms and compare those. So on this side we've got A, that's 1A. This is minus lambda lots of A. So we can factorise out an A and have that. We're just left with lambda C. And that equals lambda A plus, mu A plus mu C. So now I'm hoping you can see that actually we can equate these two bits. If one side is equal to the other, then the A bits must be equal, and as well as that, the C bits must also be equal, because one side is equal to the other. This A bit will be equal to that A bit, this C part will be equal to that C part. So let's combine this and see what we've got. So looking at the A coefficients, so the coefficient of A here is 1 minus lambda. So 1 minus lambda must equal this lambda. So if you rearrange that, add a lambda to both sides, we'll get 1 equals 2 lambda. Therefore, lambda equals a half. And then looking at the c components, we can see that lambda equals mu. Because we knew lambda's a half, they're both equal to 1/2. Based on these two bits being equal. So lambda is equal to mu, which is equal to half. I only need to remember, what was lambda, what was mu? Well, lambda was just the multiple of AC, and mu was just the multiple of how far along we go from O to B. So each multiple is a half, which means that P is halfway along OB, and P is also halfway along AC. And so P represents the midpoint of both diagonals. P is also the point where they intersect, so therefore they must intersect at the midpoint of both diagonals. So we can just conclude by writing this out in English. So therefore P is the midpoint of both diagonals, which is another way of saying that the diagonals bisect each other. And I don't know about you, I think that is quite interesting and amazing. Without even drawing a parallelogram or having to verify it with measurements, we've proven by just using abstract vector arithmetic that they must bisect each other. And we've proven it using vectors of all things. So that's question 4 completed. Final worked example, last but not least, solving this triangle problem. So we have triangle ABC, vector AB is 3i minus 2j, AC is I minus 5j, and we need to find the exact size of angle BAC in degrees. So what we're going to think about here is each side of this triangle taken separately. So AB, AC, and BC. So first of all, let's just consider AB. So for AB, we're going to draw in a line in yellow. So that's AB. Also considering from A to C in blue and B to C in green. So let's think about, first of all, from A to B. So this is from A to B, and let's use information we've been given so far. So we've been told that AB, we're going 3 along and 2 down. So in other words, 2 down. So the magnitude of this distance is 2. Now in terms of this, what we'd be interested in working out is the magnitude of A and B. In other words, the length of this side of the triangle. So the magnitude of this vector AB, which will relate precisely to the length of this line that represents AB, we just think about this as we're squaring the I component and squaring the j component and square it in the whole thing. But as you can see here, minus 2 squared is the same as 2 squared. We're effectively just working out the hypotenuse of this triangle. And if we do that, 9 plus 4, that gives us root 13. So from A to B is root 13. In the same way, let's try from A to C. So A to C, we were told about this one as well. From A to C, we're going 1 along, so this one's 1, and we're going 5 down, so this length here would be 5. And so the magnitude of from A to C is the same as finding the length of this hypotenuse here, so it's going to be 1 squared plus 5 squared, or in this vector form, it might be plus minus 5 all squared, which actually ends up being the same thing anyway. But what we got here is root 26. So therefore, from A to C, we can represent this side with root 26. Then what we need to think about is from B to C. So from B to C, we need to think about what B to C actually is. To go from B to C, what we could do is we could go from B to A, and then when we're at A, we could go from A to C. Now from B to A is the same length, the same direction as AB, but the exact opposite direction. So BA is minus AB plus AC. Why on earth would I put a times sign there? I must be tired. Apologies. I mean plus. So, minus AB. So we know what AB is. AB is this. So minus AB is going to be minus 3 minus 3 minus 2 plus from A to C, which is 1 minus 5 which is minus this becomes minus 3 minus minus 2 is plus 2 plus 1 over 5. That's going to give us minus 3 plus 1, which is minus 2, and 2 plus minus 5, I do apologise, missed out the minus there, 2 plus minus 5, which is minus 3. So therefore, the magnitude of BC is going to be the square root of minus 2 squared plus minus 3 all squared. So minus 2 squared is going to be 4, minus 3 all squared is going to be 9, so 4 plus 9, this one again is going to be root 13. So that's root 13 as well. Now we're in a position to apply, well done if you've thought about this already, to apply the cosine rule. And we want to find BAC, so we're after the angle at A, which is this one here, which I'm just going to call theta. Okay, so just remembering the cosine rule, we have A squared equals B squared plus C squared minus 2BC cos A, where A is the angle which is opposite to the side A. So if we rearrange this, we can say that A is cos minus 1 B squared plus C squared minus A squared all over 2BC. Now it's just a case of realising what's what. And so angle A, in this case, is going to be the same as angle theta, because I've called it theta. The side opposite to A is A, so opposite to our theta is this A here. So opposite to theta is root 13. And so our A, if you like, is this root 13. The other two sides do not particularly matter at all. In any order, B, let's call B root 13, and we can call C as root 26. Now, in fairness, what I'm going to do here, you could just bash it into your calculator, you're absolutely fine. I'm going to show you that this is actually an exact trig ratio. Okay, so cos minus 1, B squared, well, B is root 13, so root 13 times root 13 is just 13. C squared, C is root 26, root 26 multiplied by itself is 26. We're going to minus off A squared, so minus root 13, that just becomes 13. And all of that is going to be over 2 multiplied by b, which is root 13, multiplied by c, which is root 26. So you could just bash this into your calculator, that's absolutely fine. I'm just going to show you, just for the heck of it, how this can simplify into an exact fraction. So 13 plus 26 minus 13, we've got 26, okay? So we've got 26 on top, which I'm going to rewrite as 2 times 13. So because it's 2 times 13, I'm going to do this one as root 2 times root 13 times root 2 times root 13. By the way, if you're thinking, what on earth am I doing? Bear in mind, it could be calculated here. In fact, I'm going to do this here for you, just in case you're slightly confused as to this tangent I'm going off on. So, if you do cos minus 1, so shift cos minus 1, 13 plus 26 minus 13, all over 2, then root 13, then root 26. You should be finding, close the brackets correctly, that the angle is exactly 45 degrees. In terms of doing it this way, got 2, root 13, and root 26, again, is the same as root 2, root 13. So if you see here, there's actually lots of cancellations you can do. So root 13 cancels that root 13, another root 13 will cancel here, and again, we can cancel a root 2 with that root 2. So it's the same as cos minus 1 of a half root 2. And you should hopefully, if you could, recognise this is one of these exact trig ratios. So cos minus 1 root 2 over 2 is root 45. And I'll leave it there for now, for you to try some of these yourselves. So if you can turn to page 234, sorry, 243, I can't even read. 243, 244, exercise 11D, questions 3 to 5, then the exam type question number 6 and exam type question number 7, and then turn to page 246 and try all of 11E. Practice makes perfect. Remember that, I do mean it, and it is actually pretty much true. I say pretty much because you can never be perfect, but you can get closer and closer to it by practicing. Anyway, enough of my rambling. Please try these questions. If you get stuck, you know how to contact me. Please do. I'll see you soon. Thanks for listening. Please subscribe. Ciao for now.